Today we'll continue talking about some sublinear algorithms. And in particular, I will introduce a model called streaming algorithm, I guess, for which I'll show you some algorithms. And I mean, the idea is not necessarily to present one particular big algorithm, but rather to present you the model and kind of, tell you what is the feeling like designing algorithms for this model. And we'll see several examples of problems that, probably will get a bit more complicated, depending how fast we go. But yeah, okay, so let me start. So streaming, basically, I have to start this. So let me describe a scenario, which is kind of probably one of the first scenarios where this has been like very well formalized. But we have a router, and suppose there is traffic passing through this router, say many IPs, right? And you might want to know certain statistics about this traffic. So, for example, this would be some kind of, table of things that has happened, some kind of log. For example, how many IPs have communicated, or, how many TCP/IP connections did we make? General, you can imagine having kind of a table of this sort, and, to collect statistics, usually these tables are much bigger, right? And the idea is to kind of be able to compress this so that in very small space, so that it actually fits on the router, so that later you can compute some statistics. So the picture should really be like that, but you can imagine that this table can have millions upon millions of entries, so gigabytes of data passing through the router, whereas the router might have something like 1 megabyte, for example, right? So definitely, like, such table doesn't fit on the router, so you have to somehow be able to compress this information. And I mean, what kind of things do we want to compute, right? And we cannot store the entire table. I mean, this will be obvious, right? But we want to compute, perhaps something that, we can hope for something. Such things like, number of distinct IPs, for example, or the max frequency, and other statistics. And, imagine this as being not necessarily, being a system which, can detect intrusion detection. So if we suddenly see that, there is one IP that has much higher traffic, then, probably this is bad. Or if there is the number of distinct IPs suddenly increased a lot, maybe there is a, distributed denial of service attack, or something of that sort, right? So the question is, how to do this, right? So, first of all, let me tell you what we are not gonna do, right? So, will we solve, super hard, say, traveling salesman problem using this very small space? Well, probably not, right? Perhaps a different lecture, maybe next year. But I mean, even before going to something like MB hard problem, it's actually hard to solve even very simple problems. For example, if you want to count the number of distinct IPs. So if we want to count the number of distinct IPs, I mean, you don't have to trust me on this, right? But it's very hard. It is essentially impossible to do anything except store the entire table. So if you have billions of different IPs, then you have to have space which is roughly proportional to this billion, essentially. And if you have, so it won't fit in a much smaller space, right? So first of all, we will have to give up something, right? I mean, it's very simple problems are hard to solve. So first of all, what we'll settle is approximation. So I guess this is hopefully not already sounds familiar, especially from the previous lecture. So we'll settle for 1 plus epsilon approximation. So think of epsilon as being, we'll tolerate 1% error. So this means that epsilon is something like 0.01, okay? And what we'll settle is that this output is somewhere between the true answer and 1 plus epsilon times the true answer, right? So the output, maybe looks, roughly looking like output, right? So the idea is to get, and the algorithm will be randomized more often than not. So it means that this guarantee will be holds with probability, say, 95%. I mean, we can increase this, but there will still be some randomness usually. And think about this as essentially also a quick and dirty way to get a sense of the data. So this is kind of, first warning mechanism saying like, oh, something is happening. Some statistics has changed, for example, or we can get a rough bird eye view sense of the data. Okay. So what is this data? So first example or first scenario that I showed you is you have a router, you have data passing through the router. And in a streaming fashion, and as an algorithm, it just sees kind of data passing through, can store the entire data. It can store just a sketch or just a sense of the data. Also, another scenario that such algorithms can appear and be used is where the data is stored on a hard drive actually, and you are reading. Doing linear scan of the data. So imagine this log maybe has happened some other day. And it's really written on like big hard drive with terabytes of data, and you want to read this hard drive. So, you can do it in random access model, but this will take a lot of time because each time you seek in hard drive, it takes a lot of time. So oftentimes it is much more efficient to just read linearly through the hard drive. This will take much less time than just doing random access. So pictorially, think about this as, the algorithm sits on the CPU and maybe main memory. There is a big hard drive, and there is data that you read linearly. So it is essentially scanned, streamed through the CPU. Okay, so the CPU is a small thing, has some small memory, much smaller than hard drive, and then this hard drive just streams the entire data through the CPU, and CPU has to get a sense of the data. So compute some problem on this data that is stored here while using much smaller memory. Okay? So this is kind of the setting. So what is the data? Data can be whatever is written here. I guess network logs, but I was explaining so far. Sensor data, real-time data. Maybe search queries or I talked to a company who do this for doing statistics on serving ads, for example. So you have a lot of internet events, and you want to kind of get a sense of what has happened. So you can do this on database. If you have big database and you want to get a sense of the data, how the data set looks like. So this is kind of application areas. And yeah, so now, so this is the setting. I hope the model is clear. So if the model is not clear, now is the perfect time to ask any question about this. Yes. You can scale. It's not the most important part. You can of course scale it up or down. Just should be some approximation. Plus minus epsilon. Let's say, right? Any other questions? Okay. If not, so now what will happen is that I will, tell you about several problems. I'll tell you about several solutions. Some algorithms, will be progressively harder and harder. So, just to get a glimpse of what these algorithms look like, and they might look slightly different, but what you are used to usually. Okay. Okay. So problem number 1, counting the number of distinct elements, right? So coming back to that problem. So which I told you that you cannot compute it exactly without storing the entire table. So we shoot for much smaller space. Okay, so to state formally, compute the number of distinct elements in the stream. So trivial solution would be to have roughly space order m for m distinct elements, right? So you can store a hash table of things that you have seen, and each time you see a new element, you hash it, see if it's already there or not. And if it's not, then you discard. If it's not, then you put in the hash table. If it's already present, then you go to the next element, right? That hopefully makes sense. So what we'll see here is that we'll get order log m space approximate solution. So the space goes from roughly linear in the number of distinct elements, which can be billions, to logarithm of that. Okay, so basically it will be just one counter. So this is space in bits, actually. Okay, so just several registers kind of, would be enough for this. So there's a picture of the problem, I guess. So I have this, the number of distinct elements here is 3, right? Okay, so this is the algorithm actually. So this dates back from some of the first work in streaming algorithms from '85 due to Flageolet and Martin. So let me describe the algorithm, right? And there will be a picture. So don't treat the code. Just think about this as a reference. So the algorithm is the following. So pick a hash function from your universe of elements into the real interval 0, 1, right? So U for us is say the space of all IPs, right? So this is how many? 32 bits, right? So this is numbers from 0 to 2 to 32. Big universe. So we don't want to be linear in universe, but we'll see. Okay, so it's a hash function from the universe into 0, 1. And what we'll do is that we'll compute this min hash, which is the minimum over all elements that we have seen. So this set S is, say, all the elements in the stream, right? So we compute the minimum hash function. Okay? And the output is this. I mean, it's essentially 1 over min hash, minus 1. Minus 1 really doesn't matter that much, right? I mean, we expect this number to be large, and it's approximate, so. So this is what matters, 1 over min hash, right? So pictorially, so imagine this is the interval between 0 and 1. This is all the hash function from the elements map into this interval. So comes element 2. We compute the hash function of h of 2. It maps into some number here. Okay, so this will be the minimum. So then comes element 5. We see it here. It maps here, so the minimum will be updated to be this value, right? Then comes 7. It says like, well, we don't do anything because it's larger than the current minimum. Then more elements come, and this will be the minimum, right? Oh, for if the set of elements is this one, right? Okay, so this is the this is the algorithm, right? So analysis will fit here. Anybody has any arguments why this should work? Why should this be any approximation has any relation to the number of distinct elements? Is it a raised hand? Or? Yeah. Right. Right. But that's the intuition, yes. I mean, absolutely right. So the intuition is that this segment between 0 and the minimum hash has roughly the expected length of the segment is exactly equal to 1 over n plus 1. Okay. And there is, I can tell you exactly what is the argument, right? So imagine we have m arrows here, right? So I'll tell you the proof now. Why the expected length of this segment is 1 over m plus 1. So we have m arrows here, right? What is the expected length of this segment can be computed in the following way. We throw another arrow, the n plus 1th arrow, and what is the probability that it is the smallest? Right? It is the leftmost arrow. Well, the probability that it's leftmost arrow is exactly equal to the expected length of this segment, right? So this is on one hand. On the other hand, the probability that the n plus 1th arrow is the smallest is exactly equal to 1 divided by m plus 1. Just because any of the arrows can be the smallest with equal probability. So in particular, the m plus, if there are m plus 1 of them, so one particular one, the last one, is the leftmost with probability 1 over m plus 1. Okay? So this is the entire proof, but this expected length of the segment is 1 over m plus 1. Okay? And I guess, you can see that repeats of the same element. So if an element repeats, a zillion times, doesn't really matter, right? Because it's still the same hash function. Okay? So this is the algorithm. That's all. No questions about that? Okay, good. Right, so, the algorithms are supposed to be simple. That's a good thing, right? Okay, so this is actually idea one. I mean, there is a second idea, to do it even better. Which you think about it, it's kind of natural. So this is kind of a sense, right? I mean, like I didn't tell you exactly that this number will be precisely equal to m, but up to constant approximation, say with constant probability, it gives you the right number, so it is in the right ballpark. Okay, so there is also idea two. So idea two really, I mean, it's something of a sort of, look, we are gonna get an approximate answer anyways, so there is no reason to store this mean hash exactly. Right, okay, so this is, a real number, so, supposedly we are supposed to store it completely, wouldn't take too much space, but, you could see that, storing up to additive approximation 1 over m really didn't matter. But what you can actually do, you can store this number approximately. So if you have a number between, say, 1 and n, and you store, so think about 1 over min hash as a number between 1 and n, for example, and you want to, I mean, if you store exactly the number, it takes you log n bits, right? But if you store it up to approximation, say 2, then you need only log n bits. So officially what you'll do, this will be the new algorithm. This is, so I call it now min hash 2. So min hash 2 will be actually not the actual min hash, but it will be the number of trailing zeros in the bit representation of the hash function, hash value, sorry. So if x, for example, it's a hash value of some number, so this is some h of 2, for example, right? So zeros is the count of the zeros, so 6 in this case, right? So min hash 2 will store the, store the number of zeros of the minimum hash that we have obtained, right? Or put differently, the maximum zeros of h of index, right? Right, so I guess I should have explained kind of the way this algorithm looks like. So this is initialization, kind of, we set kind of 0 at the beginning, and we have some hash function h from our, IP addresses to 0, 1, say, right? And process, what do we do when we see some IP address? And, this if really just takes the maximum, stores the maximum number of trailing zeros of the hash function of the index. Okay? Does this make sense? Yeah? Good. So randomness, there is hash function. We don't want to use a complete, we don't have fully random hash function, so there is a question of randomness, right? So it turns out that pairwise hash function is enough. So for this, we might need something like order log n bits. So by n is the total number of entries in the stream, right? So length of the stream. So the number of elements together with the repetitions and everything, right? Okay. So so it's log n bits. If you don't count randomness together with the randomness, you need another log n bits, right? Okay. So, and you can achieve better accuracy. So far, if you go through the numbers, you'll get some constant approximation with some constant probability. You might want to get a better precision. I want not 50% error. I want maybe 1% error. So, what do you do? Well, you can repeat several times. This entire algorithm, just repeat several times, and take an estimate, the median estimate that you're all familiar now with. So you repeat, say, 1 over epsilon squared times, and with different hash functions, and it works. And actually, kind of the best algorithm that is people use in practice nowadays is something called hyperlog-log algorithm, which essentially does the same, but with just one hash function. So instead of having 1 over epsilon squared hash functions, which means that you have to do so many evaluations, it's just one hash function. The algorithm changes a bit. Don't want to go into the details now. Okay? So this was the algorithm for counting distinct number of elements. Are there questions? No? Yes? No? Okay. All right. So going on. So that was one algorithm. Going to the next problem. Next problem is max count. So suppose we want to compute not the number of distinct elements, but say what is the max count of an element that we have seen, right? So suppose the router has seen this element, IPs 2, 5, 7, 5, 5, right? This would be the table. The max frequency will be 3, right? So we would like the router at the end of the day, when it's asked the question, what is the max frequency, it will say the element 5 had frequency 3, right? So that was the worst offender, right? I mean, took a lot of traffic. Okay, so bad news. It's actually hard to distinguish whether max count is 1 or 2. So max count 1 means that there is no repetitions of any element. Max count 2 means that there is at least one element that repeated. And yeah, so distinguishing between these two cases is hard. What does it mean to be hard? Well, there is nothing else you can do but essentially store the entire table with, for each IP, how many times have we seen it? Right, so this is bad because, again, these tables are huge. They do not fit on a router. That would be really bad. So what do we do? So it turns out that we can relax the problem somewhat and solve slightly different problem, a relaxed problem. So this problem is called heavy hitters. And depending on your application, that might be sufficient, right? In either case, this is the thing that you can do. So sometimes you get what you can, you take what you can get, kind of, right? So heavy hitters. So we have. So what is the definition? So suppose we have an element that has frequency bigger than total frequency divided by some big number s, right? So s is some parameters. So the idea is, we won't be able to, if there are many elements and maybe one element repeats, another element doesn't repeat, right? This is hard. But if there is some elements that repeat really often, they really are worst offenders, create lots of traffic, right? So I want to find those, right? And these we call heavy hitters. So what kind of guarantees do we want? We want that elements with frequency bigger than total frequency. So total frequency is just the sum of these numbers, 5 in this case, right? Divided by some number s, right? And the space that we'll be using will be proportional to this factor s. Okay? So does the problem make sense? So yeah, we won't be doing max count. We'll be doing heavy hitters. Okay? Sorry, just everybody is so quiet. I'm wondering whether it's like morning or problems, or just the slides, or I'll assume it's morning, right? Okay. Okay. So I'll tell you another very popular algorithm. It's called count min. Actually, there are two algorithms. I mean, one was appeared in this paper by Charikar, Chen, and Farah Koltan, which was called count sketch. And then there is another algorithm, just slight modification, by Kormodia Muthukrishnan, called count min. I'll explain to you count min. Count sketch is roughly the same. Okay, so this will be slightly more complicated than the previous algorithm. Okay. Yeah, this is the code. Don't, again, try not to read it, but think about it as a reference. Okay, so this is a table, and in case you wonder, it has 3 rows. Just some colors are not as powerful than the others. We call this number 3L, right? And so we have so this table will be what we'll store, okay? It's called the sketch. Here it is called the sketch, right? So this is the table, 2-dimensional array, right? L rows, W columns, right? And we'll store some numbers there. Okay. So for each row, we'll have a hash function, right? So it is a hash function from our universe into W columns, right? And for each row, we'll have a hash function. Okay, so how does the algorithm work, right? So we see an element 2, right? So, we look at the stream, at the beginning, we have seen nothing, right? Beginning of the day, we see element 2, right? IP2. We say, okay, we'll update our sketch to reflect the fact that we have seen 2. Okay, so what are these arrows? These arrows correspond to the, these values of the hash function, right? So h of 1 of 2 maps into column 2, h2 of 2 maps into column 4, and the third hash function of 2 maps into this cell, first column, right? So 1 hash function per row, okay? And what do? We just increase the count in the table, right? Wherever these arrows map to, we just increase by 1. Okay, so the ones that are empty are zeros to start with, right? And whenever we see a 2, we just increase the corresponding cells. Okay. So we see a 5. Suppose hash functions look like this. These arrows correspond to where does the hash function maps 5 to into. These are the maps. We increase by 1. We see 7, increase by 1. 5, increase by 1. 5, increase by 1. Okay? And so if this was our stream, this is the hash table that we get. This is the sketch that we get. Okay? So this is how we update the sketch. Okay? And now, like how do we answer a query? So the query is, actually it provides a bit more than just have a hitter. It provides, this sketch will provide the following, we'll be able to answer the question of the form of what is the approximate frequency of an element I, right? So this is, so I described you this process, right? How to construct the sketch. So now I'll describe you this output, right? So, so for each index I or IP I, right? We want to be able to compute what is the approximately the frequency, and how do we do it? We take the element, say 2, look where does this hash function maps to, right? The same hash function, and take the minimum of numbers, of these 3 numbers. Okay, in this case it gives 1. Take 5, take minimum 3, 7, take minimum 1, and before we go to 11. So note that this is actually pretty good, right? It actually gave us exactly the numbers we wanted, right? Now, it won't always be this good. So for example, sometimes there could be an element 11, but we have not seen before in the stream. And we might ask, what is the frequency of element 11, right? And for example, this is the hash function. It will take, will compute what is the minimum of these 3 numbers. It will say 11, right? Sorry, it will say 1. So this is slightly wrong, right? This frequency. So this is just to illustrate that the algorithm is not perfect. It will error, But the general hope is that the error that it will incur will not be large. Okay. All right. So this is the algorithm, right? And next slide, analysis. I'll try to argue why does it make sense and what do we want from it. Okay. So, are there questions about the algorithm? I'll give you a second to stare at it while I drink water. Right. So, okay, so this will come in the analysis, but yes, roughly to say that it's heavy hitter, so elements whose frequency will be more than, say, total frequency. So total frequency is easy to compute, right? So if an element will have frequency much larger than total frequency divided by W, then we'll say that this is the heavy hitter. So you should think about this. I guess I should have written this right there. We'll think about L as being small essentially. Think something like log n, right? And W is this S that I mentioned in the previous slide, right? So basically, the heavy hitter element will be those for which this approximate frequency, right, of I is bigger than total frequency divided by W. Okay, so let me actually go through the analysis, right? I mean, it will appear a bit more clear which elements do we approximate well. So some elements will not be approximated well, some will be, right? And it's exactly those elements that are heavy hitters. So this is why we'll be able to detect which are those. Question? Sorry, it depends on the size of? Okay, it does not. Right, there is a hash function that maps, so it's a hash function which maps from the entire universe, which can be anything, into an array from 0 to W minus 1, say, right? Right. Oh, okay. Right. Okay. Sure. I agree. Yeah. So this is in some sense an issue, right? So when we are computing this, right? Yeah. I agree. It's an issue. Absolutely. There are ways to deal with it. It gets a bit more complicated than that. So think about this then as an algorithm that it can tell you what is called a point query, where I say, okay, I have an index I. What is approximately its frequency? Okay, so this much we can do, right, without having to iterate through this, right? But I mean, there are also ways to approximately tell you what is the possible set of heavy hitters, right? But yeah, great question. I mean, this is something that I wanted to swipe under the carpet. Not mentioned, but it is a great question, especially if you do want to find heavy hitters. You do hit this problem. You don't want to iterate. That's true. Okay, so analysis. So let's look some element 5, right? So we want to look at this minimum, right? So we take element 5, right? What we compute some approximate frequency of this 5, right? And what do we do is like, well, we take a look at all these free cells. We take the minimum of them. Right? And somehow we want to argue that this minimum is approximately equal to the right frequency. Okay? So let's take this, one particular cell, and let's see, what is this number, right? I mean, what number do we get in this cell? So if element 5 maps into here, right? So this means that this number has at least the frequency, the real frequency of 5, plus some extra stuff. The extra stuff comes from the fact that there could be other elements that also mapped into this cell that increase the count, right? And then, in some sense, artificially increasing the count for 5. All right, so this is what we call by extra mass. So extra mass means that, like some spurious increases of the counter just because some other elements, not 5, has hashed into there and increased the count. And what is this extra mass? So the expected, at least, in expectation kind of, the expected extra mass is at most total mass divided by W. Okay, does this, why is this happening? Exactly. Yeah, so for each, exactly, right? Total mass means, the frequency, the total frequency of all our elements, right? So for each particular element which is not 5, the probability that it falls into this cell is exactly 1 over W. Sorry? Yeah. No. So fix any cell. Fix any cell. You're right that if we were to condition on int being minimum. No, so this argument is for any cell where the hash function, where this arrow maps to from 5. So this is true on expectation if for this cell, for this cell, for this cell, right? So it is for each row this is true, right? Okay, I mean the idea is that imagine kind of we have I know each element comes with a bunch of balls kind of, right? And for each, and these balls are colored, right? I mean, so the color meaning this number 5, right? And I say that all the red balls will go into bin number 1, right? And but all the other colors can go into any of the particular bins, right? So they either can go also in this bin or can go into some other bins, right? So what is the expected number, the fraction of the total of all the balls that will come into this bin? Well, this is total number of balls divided by the number of bins, roughly, right? So the number of bins is W. So in expectation, at least, this extra mass is at most total mass divided by W, right? And this is the main thing, right? I mean, this is exactly what we wanted, right? That the error. So I mean, this extra mass is what incurs the error, right? We want this error to be bounded, right? So, total frequency divided by W, right? I mean, this will be the error for each particular cell. There is a question? Yeah. Yes, absolutely right. Yeah. This is why we cannot do max frequency. This is. Yeah, so for skewed distributions, depending on what exactly you mean by skewed, it can detect the heaviest elements, right? But yes, exactly. I mean, in some sense, this algorithm gets you an additive error, where this additive error is really this total frequency divided by W. Right? Okay, so let me just finish the analysis. So by Jevashev, this is true with probability at least half. So maybe this expected mass will be, say, at most 2 times total mass divided by W, right? And if we repeat this L times, this is why we have a bunch of rows. So if we repeat L, which is say order log M, and take the minimum, then we get high probability statement. So this means that the minimum of over L of such estimators will get the approximate, will have total extra mass, really at most total mass divided by W with high probability, even over all M possible elements. Question? Mm-hmm. Sure, yeah. Oh, you mean that we can show a tighter analysis? Is this what you... Right. This is true. I mean that you might be able to prove a slightly tighter analysis, right? Yeah. So I'm showing just ballpark, right? But that's true. And yeah, just to complete with heavy hitters, like we can compute the actual heavy hitters from this table frequency that we have computed. Okay. So this finishes the heavy hitters part. Does it make sense? Okay. So let me go on. Let me show you some other problem-free moments. So suppose I want to compute what is called a moment of frequency. So basically things like what is the variance, for example, of frequencies. Right? So f of I is the frequency of element I. I want to compute, say, the second moment where from this I will be able to compute, say, the variance of the frequency. Right? Where in some cases one might be interested in computing even higher moments, basically the sum of frequencies to higher power. And sometimes if you think about these frequencies as some empirical distribution, we might want to compute some other properties of a distribution. So for example, for k equals 3, k equals 4, there's like some particular types of properties, right, called skewness, kurtosis, right? So this is like one reason you might want to compute higher moments. Another reason is that computing higher moment for higher k can be a different proxy for computing the maximum. So max frequency, it's a hard problem, right? So you might want to to solve some problems that kind of approximate it as well as possible, right? Heavy hitters is one approach. Another approach is to compute what is called this higher moment, right? So and why does it make sense is that if we take the limit of k goes to infinity of of the kth norm of the frequencies, then we exactly get the max frequency, right? So let me just show you an example. So imagine this is the table. So if we compute the 2 norm, then the second moment, we get this number. This is the root of f2. It gets you something like 3.74. It's some overestimate of the max element, which is 3 max frequency. So you can compute f4, the fourth moment. Compute the fourth root of f4, it gets you 3.15, say, right? So this is a better approximation to the max element than this one, right? Now, jumping a bit ahead, what will happen is that the higher the k, the harder it is to compute this, the more space you have. So you can think about this as putting it differently, saying, OK, I have this much space. What is the best approximation I can compute? What is the highest k I can go and still compute it faithfully, and this is this principle of I take what I can get, right? So I have this much space, give me the best thing that you can get using this much space. Okay. All right. So let me start with f2 moment. So f2 moment again is computing this number. Okay. So how do we do it? And this you should know. Any guesses? So the question is, how to compute in this streaming model to compute the second moment. I mean, it is. If you think that it's too simple, then yes, it is. Sorry. Okay. So let me write. So for each element I, you map into some value h of I, which is in the interval between -1 and 1, or 1, I say. So -1, 1. Okay. Sum of times, I guess, frequency of I, right? What the entire thing is squared, right? Yeah. Yeah, you're right. Yes. So basically, this is, we can just use Johnson-Strauss lemma that we've seen in the first lecture. Thanks. So I mean, this is one way to do it, and this is essentially Johnson-Strauss lemma where we have just one dimension. The output is one dimension only, right? So just to write it out exactly, this is something that you have seen already in the first lecture. So the sketch will be if f is the frequency and g is this projection matrix. So basically, it's k by n matrix of Gaussian entries, or it's okay if it's not are Gaussian but plus minus ones. And this is the sketch, right? So we think of k as being very small. I mean, it will be something like 1 over epsilon squared to get 1 plus epsilon approximation. And this is the sketch. So the sketch is really small. It's constant number of counters, essentially. And yeah. So, just for the heck of it, right? I mean, the update on element I, how will it look like, right? So so this is the sketch that we need to have after the update, and this is g of f is the sketch that we have because of linearity, right? So obtaining the new sketch is just equal to the old sketch plus this thing, right? So what is this thing? So ei is just the basis element, meaning that it is a bunch of zeros with 1 on coordinate I, right? And you just take this matrix G, multiply by I, right? And you add it to the sketch. Okay. And you do not need to store this entire matrix G explicitly. I mean, otherwise it would be too big, much bigger than n. So it would be kind of pretty bad if our G will be even larger than what we are trying to save, kind of, bigger than the data. But you can compute this G as essentially, as a hash function, essentially, right? So obviously you need four-wise independence. Yeah, and you can achieve even better algorithm with. If indeed instead of Gaussian entries you have plus minus ones, and you can also achieve update time which is absolute constant. So you really kind of on one element you just increase or decrease some counter just one, right? Not k of m. Time to update. Okay, so that's just to say that this is doable, right? I mean with the techniques from the previous lecture, right? So this is part of the reason, this is concrete application, part of the reason why dimensionality reduction is so cool, right? And the one that you had on your homework for Manhattan distance, gives you exactly this same type of sketch, right? I mean, is also useful for streaming algorithm. And it appeared kind of exactly for this application first time. All right, so let me, so I'll try to give you a glimpse of f of k, right? In a few minutes that remain. So I started at 40 past, right? All right, so yeah, I'll finish in 5 minutes. So we started a bit late, right? So we will finish at 30 past. Sounds good? Or when did we start? Okay. All right. So before about saying something else, let me actually give you another scenario. So this is not a problem. This is another scenario where I want to make a point, essentially, right? And the point will be clear. So let me give you another scenario where such streaming algorithms appear. I mean, it's a modification of the scenario that I talked about at the beginning of the lecture, right? It is the following. It's essentially, the idea is, suppose we just don't have just one router where all the data passes through the router, right? We actually have a bunch of routers. We have some cloud. So we have some cloud. We have maybe 2 routers, right? And there is traffic that passes, for example, through this network, right? And it could be that, so we have some things passing through the network. Maybe some packets are lost. Maybe some packets somehow appear, right? And we might consider the problem where we have, like this is the router. This is the traffic that passed through this router. This is the traffic that passed through this router, right? I want to see what is the difference, right? How many packets did appeared? How many packets got lost, for example? Can we have statistics on the difference of the traffic? Okay. Or another thing is that maybe there is a different points of entry into our cloud, right? And we want to say that, well, we want the statistics on the aggregate traffic. So there is traffic here and here and here. I want the statistics on the entire aggregate of this. Okay, and again, these tables should, well, I mean, we should be able to sketch these things so that they fit on the router to be able to compute these differences or sums of the traffic. Okay? And the idea is something that we already actually have. So the linearity is the power. So it's really good when the sketches are linear, right? So just like we've just seen for this 2 norm, right? The sketch was linear, right? Because so the sketch was equal to some matrix, right? Times frequency. So this is our input, right? And this is the sketch looks like something times our vector of input, right? And the good part is that it is linear. So basically, you can compute sketch on each of the separate data separately, and then the sum of the sketches is equal to the sketch of the sums of the data, and the same with say differences, right? The difference of the sketches will give you the sketch of the difference of the data. Okay, and I think. So let me just conclude this lecture with just concluding slide. So I skipped the FK, but it will be in the lectures online. So there is actually a lot of work in streaming. Like some of the first algorithms appeared in '85, that I showed you the Flageolet-Martin algorithm for counting distinct number of elements, right? Since then, there are lots of work. There are surveys. There is even there is a website which has a lot of open questions listed there. Take a look. And the cool part is that like people have looked about solving a lot of problems in this model, right? So I talked about frequencies of IPs, but you can imagine that there are, for example, graphs, and you want to solve some graph problems. in the streaming model. Or you have some, you want to solve some regression problems. Or solving some equations, right? And the cool part is that people have thought about a lot of different algorithms in this model. And the cool part is that this is a model where you say like, okay, this is the constraints I have. Here is the problem. Let's solve, right? And people have thought about this, right? For these algorithms, for this model, right? The cool part is that thinking about this model actually went on and gave back kind of algorithms in the usual kind of Turing sense. So meaning that thinking about algorithms in this model have led algorithms led to better algorithms in the standard model of computation. So for example, very recently, essentially streaming IDs are very useful for computing what is called dynamic graph connectivity. So dynamic graph connectivity is a data structure question where you have a big graph. And dynamically you add, delete edges. You want to always be able to answer quickly whether some pair of nodes S and T are connected, right? So this can be solved using some of the streaming technology, actually, right? And another also kind of something that you can see that especially, for example, this year has become just blossomed was computing fast sparse regression. So these are some metrics questions that are very useful for machine learning, right? Numerical analysis, numerical algorithms, kind of. And it was really kind of the ideas from the streaming algorithms have led to better algorithms in this area. Okay, I'll end this lecture here. See you in 10 minutes. Okay, so let me go into the last lecture. This lecture will actually be somewhat similar structure as the previous lecture. So I'll tell you about some particular model for algorithms, and I'll show you some particular ways to solve algorithms there, right? So one word of warning. This is kind of this is okay, at least in my opinion, much less understood than, say, streaming. It has been around, in this form at least, for much less years. And this is something that, I have kind of studied myself only recently, right? But I don't know. This is kind of, very new, very cool, kind of, I find, right? So this is why I wanted to tell you about this, right? Because this is like really, really at the front end, yeah. Sure, yeah. Sure, yeah. All right. So let me go, just, general motivation, right? So, like in the previous lecture, right, what we had is that we had one computer, kind of one CPU, and all the data passed through this, right? So you at least still had to do a linear scan for the data, right? And, as you've seen in especially Mihai's lecture and some other lectures, right? There is these parallel models where we have a bunch of machines and we hope to attack them in parallel at the same time, right? So rather than scanning through it just with one machine, even that takes time, right? So now we have a lot of machines and we still want to do something cool, some cool algorithmics, right? And I shall say, the lectures are, focused on kind of theory. So basically, like on algorithmic ideas, right? This is really the focus that I want to, put on. Okay, so we have data, cannot be seen by one machine, right? It's very many machines looking at it, right? Remember, the cards, and there are systems that essentially implement it, right? And I will explain, some particular formalization of the model that could be extracted from these actual, real systems. And again, like we focus on algorithmic tools, and this is really, really incipient, right? This is something just happening now. So the types of problems that I want to mention, again, some will be simpler, some will be slightly harder, but these are the type of questions that I want to discuss in this lecture. I mean, don't worry, I mean, like many of them will be kind of simple. So I'll just briefly, this is why it's 0, right? Briefly again discuss a second moment of the frequency and essentially observe that in this model it is again very simple to compute it, right? And then I'll go into some questions like fundamental sorting, connectivity, meaning spanning tree, in general very many more, but this is something I want to discuss in this lecture. Okay, so computational model. So let me talk, like this is here I do want to put bounds. I want to have, order n kind of stuff, right? I mean, asymptotic notation and everything. So computational model, let me exactly describe what we have, what we don't have, right? So think about the following way. We have m machines. Each machine has space S. And we think about this, that m times S is roughly equal to the order input size. So first of all, m times S has to be at least the size of the input, right? Otherwise, we don't have space to store the input. What I'm saying is that we will not have much more space than, how big the input is, right? This is mostly because, the data is large. Replicating the data by a large factor is essentially prohibitive, not possible, right? So, pictorially, we have, say, a bunch of machines. We have, say, n input elements. So these n input elements are, think of this as, the log traffic kind of, and you have, each event is one of these elements. Or if we sort n elements, n numbers, right, then each element is a number. If we have a graph and we want to do connectivity, each element is a node or edge, right? Okay, so how does it start? So, this is the cloud of elements. Think of this as either the numbers to sort or, say, vertices of the graph or something of the sort. And, at the beginning, they're really distributed arbitrarily between these machines. Okay, this is the model, right? I mean, basically, each machine roughly gets, 1 over m fraction of the input. Okay? So what happens, the computation goes in rounds. So in one round, each machine takes its input, cranks on it, right, does whatever it wants, and then, after it did this, it communicates. And there is the communication stage, right? In communication, it is all-to-wall. Again, right, this is a model, right? I mean, it is, communication is wall-to-wall, so, they decide to communicate something, they can communicate to any machine whatever it wants, essentially how much it wants, with some restraints. So, and these rounds can, we repeat several of these rounds. And at the end, we get our output, right? And this output often is also distributed, right? So if we sort n numbers, the output is also of a size, has size n. So it's not stored on one machine, it's also stored across many machines, right? So these edges are the output, for example, right? So again, oftentimes the output might be of the size of the input, right? Doesn't fit on one machine. So the output is also stored distributedly, and the main focus here will become on rounds, right? So as Mihai has mentioned already, is that these kind of shuffles, right, where everybody communicates to everybody, is really expensive. So we want to really minimize the number of such stages. Okay? And this is, think of this like, what is the main, there is a bunch of parameters. What is the main parameter we care about? This will be the parameter that we care about. Okay? So let me just, repeat this. So in general, what we'll want, that the number of these rounds is constant. Something like 3 or 4. Okay? And so again, like at the beginning, here I just said m and s. I'll put some bounds on m and s, right? That actually, like will make sense. It's not always possible to get this, in any reasonable thing, to get these rounds if space is too small. So we'll put a bound of a sort of that space is at least root n. Why does space at least root n make sense? I mean, first of all, I guess in practice, usually you have a space much more than the number of machines, right? But it's also, for example, this is implied by the fact that the space is at least m. So if we say, in the situation where each machine has enough space to store a routing table for all the machine in the, collection of the machines that compute, right? This means that the space is at least m, and given that s times m is equal to n, number of elements, this implies that space has to be at least square root of n. Okay, so this is some motivation where, if you didn't follow this, then, just assume that the space is some at least polynomial in n. So it is root n. Okay? And I mean, we also need to bound the resources bound, all the resources of a machine will be bounded by S, right? So if I have space S, this means that if this is the machine, right, and if this is the shuffle stage, right, the output here, right, this cross-section, in total, has to be of order S. So the sum of the lengths of the messages that one machine sends in one round has to be upper bounded by the space S, and the same with the input, right? So the number of the messages that one machine receives has to be also be bounded by S. So in particular, what is not allowed is that one machine broadcasts to everybody. Okay? This is not allowed. I mean, if this is, this particular broadcast can be modeled, say, in 2 steps, for example, right? But it is not, it's just more convenient to define it this way. Okay, so, and, how much, there is another question that, it doesn't appear on the slide, but, how much runtime, so how much runtime does one machine does with its local data? So, in general, I mean, so this, I'll leave this mostly unspecified, right? But, in general, you want, the algorithms that, run in kind of linear time or near linear time. I mean, mostly we'll get this by default because, the other parts of the system will be more complicated, right? I mean, it's more complicated to guarantee the number of rounds, right? So getting runtime per machine faster is a different question. And it's already in the realm of questions that we know, right? We want to compute some computational problem, right? And there is some input, and it's just one machine. How much time does it take? It's like, well, take your algorithms textbook and try to do the best. Okay, and so this model is very similar to what was called the bulk synchronous parallel model, introduced by Leslie Valiant in the 90s. Though it didn't necessarily pick up too much at that moment, but more recently, after the MapReduce system has appeared, some researchers have picked up and tried to introduce these models, and so this model is essentially the model of basically Goodrich-Sichinava-Zhang, which is just a modification of this. I mean, well, not just, but it's a modification of Karlov, Surya, and Vasilevsky model, but we call it MapReduce framework. But this is the model. Okay. Other questions about the model? So again, I mean, just to repeat, right? I mean, this is the model, and from now on, till the end of the lecture, we'll basically go through a bunch of problems and just see what are kind of algorithmic tools we can play with here. So no questions about the model. Okay. All right. So PRAMs. So first of all, this, as I mentioned, so in 90s there was a lot of work on parallel RAMs. So people have thought about like, oh, what can we do in parallel, right? And we did. There was a bunch of work in 80s and 90s that solved a lot of problems in parallel. Things like connectivity, for example, and it's very nice work, right? And there are some bounds, right? And these papers, right? they have shown that you can essentially simulate these PRAM algorithms in this MapReduce framework. Okay, you can simulate, in the number of rounds, which is roughly, so this R is the number of rounds, roughly proportional to the what was called in PRAMs parallel time. So this is kind of under assumption you have a bunch of processors, how much time, time steps, parallel time steps will it take to complete the computation, right? And you can do this, right? In essentially, the craziest PRAM model, which is called CRCW, you can still simulate it. So, which is really good. This means that, you can take, decades of research into algorithms and port it here, and it's like, oh, we have a bunch of algorithms immediately, right? So this is all good, except for the bad news that you already, I presume, read, is that often the number of rounds there is logarithmic. And often this is probably the best. So the number of rounds will be logarithmic. Here, really, so the big difference, right, why is this a new question, is that we want the number of rounds to be constant and not logarithmic. So we can use these algorithms, except that we'll get logarithmic rounds. Can we do better, right? This is the question. And the model is sufficient, is somewhat different from this PRAM model, but it will allow us room to actually design algorithms that do have constant number of rounds, as we'll see. Okay. So let me start actually with something simple, well, hopefully simple. Again, statistics. So suppose we want to solve the same problem that I mentioned at the end of the previous lecture. So we have some, say, the traffic doesn't pass through the router, but it is stored as a log on a hard drive, right? So the router passes and it just stores on the hard drive. Now you have this network log stored across many machines, and you want to compute, say, some moments, say, second moment variance, right? So how do we do it? This is it. Perfect. Thanks. Yes. Yeah. Exactly. So we compute, each machine computes the sketch of its local data, right? The sketch is small. We send to one dedicated machine, the victim, call it machine one, and machine 1 will just add up the sketches to get the sketch of the entire data, and here we again use the linearity of the sketch. Right, so in the second moment, the sketch was linear, it's just Gaussian times the frequency, right? So this equality holds. Thanks. So this was simple. And so basically all the streaming algorithms where we have linear sketches do port here just like that, right? So this is cool. Except that, in sketches, there are many other problems that are hard. So, okay, next. Let's go into something more interesting, so sorting. Okay, so, as far as I know at least, right, and I know there are people in the audience who can correct me, right? So for PRAMs, the best algorithm has to be at least log n, perhaps log n divided by log n. Number of rounds. So this is not good. We want constant number of rounds. So how does it work? So this will, I'll describe the algorithm here. We will go through it, and it's if you want to remember one algorithm from here and you haven't seen this, right, then definitely focus here, right? And this is the algorithm to remember. And it will be simple, right? It's not something fancy. You'll see. But just to make it even simpler, let me just focus on one particular case. So suppose the space is really equal to n to power 2/3, right? So the space is somewhat larger than the number of machines, right? So remember that S times M is equal to n. So this works out. N is the number of elements to sort. Okay. So what do we do? so each machine in parallel picks each element, as a chosen element, let's call it at the moment, with probability something like root n by n. I mean, basically 1 over root n, right? But it's easier to see from here that the total number of chosen elements will be root n. So pictorially, let's say this is the line, right? So this line means that each point on the line is a different number that has to be sorted, right? And each machine will have a random subset, arbitrary subset of this line, right? So all these, points on this line are distributed across lots of machines. Okay? So each machine can completely independently, without any communication, pick a bunch of elements, right? It calls chosen. So let's suppose these are the chosen elements, and there are root n of them. Okay? So now what happens is that we take all these elements, each machine, and sends all these elements to one machine. Okay? So in particular, machine number 1, will get root n elements, right? Which is much less than its space. So it's all fine. And it has root n elements, which is, compared to its space available, right? It's a very small number, right? So it sorts them, and it picks some equidistance pivots, as we call them, so that we divide this entire segment in roughly equal segments, right? So it will be something like this. Okay, so so we had a bunch of chosen elements, right? And we choose these pivots, right? If you really want, I'll be lying, but if you really want, you can think about this as, these chosen elements being the same. Basically, the chosen elements as being the same as pivots, right? If you really want, right? I make it slightly more complicated because if we just choose completely random elements, right, the segments, the ranges that we get are not, will not be quite equidistant, right? This makes us, our ranges really have the right length, more or less. So the idea being that, think of this as like, just one step of radix sort, where we pick some, pivots and we partition according to them, so that each range will roughly be capture order n to 2/3 elements, right? So there are n to 1/3 of them. So what happens now that the number of pivots is not written there. The number of pivots will be exactly m minus 1, right? So that the ranges between pivots are equal to m. Okay, so this is it. And then what do? We send. So this is what machine 1 did, right? It just selected these pivots, right? Which partitioned our segment of all the numbers into equal segments, and we just send these pivots to all machines. Note that the number of pivots is roughly n to 1/3, right? So this is, this is roughly n to 1/3, which is much less than the space has. So it's trivial amount of space essentially. And now each machine sends all. So each machine now has the pivots. It takes all its local elements and it says that, well, I know these elements are in this range, so I'll send them to machine 1, right? These elements are in second range, I'll send to machine 2, and so forth. And we'll send them. Sorry? Sure, yeah, so, yeah, assume all elements are distinct. You have to be slightly more careful if the elements repeat, but, assume they're all different. Okay, so just to give kind of an example. So imagine, so one way by way to sorting yesterday with cards, right? So everybody remembers the cards from yesterday, right? So one way to sort with 4 people was to assign how it is called, club, a color, right? The suit to a person, and then all the other person would have sent the cards with the corresponding suit to the respective person, and that person, there would be one person responsible, say, for sorting the spades, somebody responsible for sorting the diamonds, and so forth, right? So these pivots are essentially the equivalent of deciding, how do we partition these suits. Okay. So first of all, let me note that there are 3 rounds of communication. In particular, these are the rounds, right? So this is, just each machine chooses some elements, sends to one machine. Then there is a step where each one sends all the pivots to all machines. Know that it's a lot of communication here, for example. Also, it's a lot of communication in this step, where each machine sends all its elements in range I to the machine responsible for that range. Okay, so this is the algorithm. Are there questions about the algorithm? Right? Mihai, yes. Sorry? Pivots, yeah. So pivots. Pivots. So we have a bunch of random numbers, right? So you just sort those numbers, and you take, you need to choose, for example, the fourth. Say, suppose the number of machines were to be 4. We would choose, basically, if the number of pivots is, say, p, right? We'll choose p over 4 to be first pivot, p over 2 to be second pivot, p over 3/4 p to be the third pivot. Yeah. So the pivots is you sort the numbers, and now you choose if there are, if you just one pivot, you pick the middle, right? If there are 2 pivots, you partition this into 3 segments, and you take the corresponding rank, right? Mihai, you had a question? Cool. I see. Cool. So if people didn't hear that, Mihai just said that this is essentially the sorting algorithm in dryad link. So this is not just a theoretical algorithm. In Hadoop too. Okay, cool. All right. So good, right? So we're doing so. Well, I mean, okay. I found about this algorithm from Mihai, so it's not a coincidence. Okay. So is the algorithm clear? Yeah. Okay. So let's continue. So this is, really, this is one of the main messages of this lecture, right? It's a simple algorithm, but just to see. So we have 3 rounds, right? This is really cool. In parallel, if we were to use kind of standard parallel algorithms, we'd get much more. We'd get essentially logarithmic number of rounds. Okay. So let me go further. The problem is, so now we'll switch to actually graph algorithms, just to play with some more complicated objects. Let me go for a different example. So this is the example of graph connectivity. All right, so graph connectivity, let me essentially partition them into 2 types of regimes, right? So the types of regimes are mostly kind of what is the relation of the number of edges to the number of nodes to the space per machine. So just to, I guess, not confuse people too much, so n will continue to be, n will continue to be the number of will be the number of vertices, right? So the input size is the number of edges, right? Not the number of vertices. So because of that, S can actually be larger than n to 1 plus epsilon, right? So S is somewhere between the number of edges and this, right? And this case we call dense, right? In particular, this condition implies that the number of edges is at least n to 1 plus epsilon. So the number of edges is polynomially larger than the number of vertices. Okay, so we call this case dense, all right? So the interesting part is that you can do, in this situation, if this is really kind of the setting of the parameters, you can solve the connectivity in order 1 over epsilon rounds. So by the way, connectivity, I mean, let's say, S from, given two nodes S and T, tell me whether there is a path from S to T. Yeah, sorry, forgot to define. Okay, all right. So I do have, I didn't really prepare to explain this algorithm, right? But it's relatively simple, actually, right? I mean, it might look more complicated than it is, but really what happens is what is called filtering, where imagine, the really trick is the following, right? So imagine you have a lot of edges, right? They're distributed across many machines, right? And one machine, so each particular machine gets n to 1 plus epsilon edges, right? So it has space S, it will have these many edges, right? And it will have n to 1 plus epsilon edges. So what happens in this situation is that and there is a lot of hover graph out there, right? If I just have a subset of the edges, right? But the subset of edges is much, much, much larger than the number of vertices. And I really care only about connectivity. This means that I can throw out a lot of edges, right? I can throw out most of the edges, just retain at most n minus 1 edges, right? Minimum spanning forest, right? Spanning tree. And those edges won't change the connectivity. Right? So this means that just without any communication, even in the first step, the machines can throw out a fraction of roughly a fraction of 1 over n to power epsilon of edges. Just in one step without any communication. Right? So you throw out a lot of edges, you reduce your input. And what you can do, now you can communicate so that you compress. So this means that every machine will have just a few, the data is now sparsely kind of distributed with machines. You can take all these edges, again, put on a few machines, load them up to the maximum amount of space, and again, repeat this, right? Meaning throw a lot of edges. Just take the minimum spanning tree on the local data, again, throw away this fraction of edges. And basically, in 1 over epsilon rounds, you'll be done. Right? So, if you didn't follow this, then, it's fine. But the idea is really kind of, like, what you can do is just filter out, meaning that you can repeatedly throw out your input until you get to a state where your input fits on a machine, and then you solve it. All right? What I consider, so very interesting case, that I consider is the sparse case where really the space per machine is much less than n. So this kind of filtering won't work. We can't, most likely we won't be able to throw any edge if we just see much less than n edges. Okay? And it is a hard, big open question in this area to see if one can do connectivity with less than log n rounds. So, and really kind of a hard case, at least, hard case is really known, right? Obvious, is that, even the following, distinguishing these two cases appears very hard. Below than log n rounds. So one case is where you have a big cycle. So this is the graph, where you have two smaller cycles, right, of half length. So distinguishing these two cases in less than log n rounds appears very hard. And really cool question. I mean, I don't know what is the answer. I should mention that log n rounds is achievable exactly by using one of these parallel PRAM algorithm, right, known from 80s. And it's an algorithm. It's not trivial. I mean, don't expect to kind of see it immediately. But you know, I don't want to go for it. It's a cool, you know, it's a cool algorithm. You can take a look. And yeah, and for example, you know, what is the other approach to the connectivity, right? Another approach is just to simulate BFS algorithm, right? And you know, from what people tell me that they tried to implement this BFS algorithm on real graphs, and try to use this log n rounds algorithm, and they say that, well, this log n rounds algorithm actually runs slower than the trivial BFS in some sense. So be really cool. I don't know. So this is the problem. Okay, and so actually, I mean, this is what I wanted to talk about connectivity. Really point out, I guess it's a hard question. So now I guess I want to tell you about something else, some other situation that actually we have been working on. Very recent. This is kind of actually unpublished work, right? So we started thinking about so this is actually a group of problems. So this is problems 3. So this is the situation where kind of motivated by this by the fact that even connectivity on regular graphs is hard. So we became curious to say, what if these graphs actually arise from some particular setting? So they arise from a geometric graph. So what does it mean? So we have, so it is the same questions, kind of basic graph questions, but in the situation where the graph is defined the following way. We have endpoints in, say, d-dimensional Euclidean space, and the distance, so think of it as a fully connected graph, and the distance between each 2 points is defined implicitly by the distance between those 2 points, right? So now you can think about questions like minimum spanning tree, for example. So let me focus on minimum spanning tree. So minimum spanning tree on this graph, on this set of points, looks like this. Note that the input here is really just endpoints, right? Even though it defines implicitly n squared edges graph, right? And let me just give you a bit of motivation. Why minimum? So minimum spanning tree. I mean, there are several answers why I find at least this interesting. So first, one of them is that minimum spanning tree is actually kind of the next interesting problem after connectivity in this setting. So connectivity in this graph is not interesting, right? Because we define it to be connected, right? So what is the more next interesting questions is say computing minimum spanning tree, and it actually corresponds. I mean, it is a way to give clustering. So motivation. Think about these nodes actually, this graph arising from one of these, say, machine learning kind of settings where, going back to the really first lecture, where we have some kind of images, for example, we want to do some clustering of them, for example, and we take these images, we somehow embed them into d-dimensional Euclidean space, and we have some, the Euclidean distance between these 2 points corresponds to the similarity between these images, and minimum spanning tree gives a way to cluster. It corresponds actually to agglomerative hierarchical clustering, which is one way to cluster data, right? I mean, if you have a big data set, you want to cluster it somehow, this is essentially minimum spanning tree computation problem. Okay. So, what do we get? So again, I mean, this is something that I've been working recently with Sasha Nikolov, Krzysztof Honak, and Grigory Rosavtsev, who actually participated in this school in previous editions. So he was interning with us. Yeah, remember, apply for internships. Can work on some cool algorithms. So what I want to show that we can get again 1 plus epsilon approximation algorithm for this problem for minimum spanning tree in constant number of rounds. There is some restriction on epsilon. It cannot be too small, right? So for some fixed approximation, at least, right? Depends on n, I guess. We can solve this in constant number of rounds. And actually, I mean, this kind of algorithm was inspired by some streaming work that people did before, in particular, an algorithm of Piotr Inding. Though in streaming, I mean, one big difference to stream, I mean, like, even though it is related, one big difference in streaming is that in streaming, there isn't even a way to output a big spanning tree, right? So in streaming, remember that we take a big data, lots of data, and we kind of store some small sketch, right? So that small sketch cannot possibly store a tree, right? It will, so actually the streaming work, what it stored was the cost of the tree. So there is some streaming work to approximate the cost of the tree. Anyway. Can ignore that if you want. I guess one message of kind of this direction is that even though graph algorithms tend to be hard, especially in the sparse case, in these parallel models, if we have some geometric information, meaning that we have this graph, we can embed immerse it into some, say, Euclidean space, then the problems becomes much more tractable for parallel computation. Okay, and for any s bigger than root n. So right. So again, m times s is equal to order n, right? And for s bigger than root n. I mean, if you want, I mean, if this is confusing, right? Another way to state the results is that the number of rounds is equal to order of logarithm of n base s. Okay, so if s is something like root n, this is constant. Okay. Any other questions? I didn't implement it. Oh, no, the number of rounds, I mean, you'll see it's, I don't know, it's 4 or 5, something of the sort. It's, you'll see the algorithm. So, I mean, the algorithm, I consider it to be simple, right? It still might not mean, I don't know if it's practical or not, right? But, I mean, this is something like, this is really a work in progress, right? This is, I mean, it's mostly the idea is to showcase, what is happening, kind of. But good question. I mean, I hope that it leads to some practical algorithms at some moment, sooner or later. All right. So in general, I mean, I think about this as being a general approach to solving this kind of geometric questions. So, the other geometric questions are things like minimum traveling salesman person or F-over distance. And I hope you heard about at least the TSP problem. So in general, so it's a general approach that kind of works with modifications for all of them. It goes back to space partitionings, to things that we've seen in the first lecture. And the idea is to be able to partition the space hierarchically in a nice way. We'll see later what it means to be nice, but think of it as, say, some kind of recursive quad tree type stuff. And what we'll do is that in each part, so actually there should be some pictures. So there is a color missing. This is not gonna be too nice. Let me try to do something. Good. Here's the color. Okay, so this is the space. So we partition the space somehow nicely hierarchically. Okay, this is hierarchy, the next level of hierarchy. What do we do is, so here is the tree corresponding to this recursive partitioning. And so, this is the big blob, this is kind of the three kind of medium-sized blobs, these are kind of recursive. And the computation will proceed from bottom up, essentially. And what it does is that, suppose this, so this is the space partitioning kind of. So this is the Euclidean, d-dimensional Euclidean space, right? We partition it. So we have points in each of these blobs that appear. And essentially what will happen is that we'll partition it such that each of these blobs, more or less, will capture the number of points which is less than s, right? So each of these small partitions will fit on one machine, right? And we will, distribute the points that way, and then each machine kind of will have a bunch of points, right? So there are on each of these kind of distributed machines, right? So will be these machines will kind of go over these over these parts of the tree, kind of, or these nodes of the tree, right? And there is some computation to be done here on this node. And what we do is that we essentially take this bunch of points, which are kind of, they are geometrically collocated, they're kind of near to each other, right? According to these partitions, we compute some pseudo solution. And then they take this pseudo solution, compute a sketch, which means that it takes much, much less space than what it used to be. Think of this as, the number of points here initially will be s, right, root n, for example. When they compress it, and they get these stars, which are these sketches, each of these sketch will be, think of this as logarithmic space, right, or constant space, really small, right? And then these sketches will correspond to this node, will be kind of input to this node. And when the next machine comes, takes care of this node, it will take a bunch of stars and use these kind of sketches to compute the next, the next partial solution, pseudo solution, and produce the sketch for the next level. So the number of levels here in this tree, in this partitioning, will be constant. Okay, so let me give you examples. Okay, this red rectangle should be around this compute actually. So somehow things moved. So let me. Sorry. Okay. So ignore the red rectangle since we are kind of shifted down. So I mean, the questions that we need to answer, basically. So this is a general approach, right? It sounds very fuzzy, kind of, right? So I need to explain to you how to partition the space, how to compute a pseudo solution, and how to sketch this pseudo solution. So, I mean, think of it like, it's intuitive kind of explanation here, right? I mean, we won't go too deeply into the algorithm. So let me let me describe, sorry, I mean, this rectangle should be, the red rectangle should be a bit higher. So let me explain how to partition the space hierarchy in a nice way. So, we can use quad trees, right, as I already alluded to. I mean, it will be some recursive quad tree, okay? How to compute a pseudo solution into the problem? We'll actually, we'll have a bunch of points, a small subset of the points. We'll compute a minimum spanning tree on those points. Sounds reasonable, right? And pseudo solution. The sketch of a pseudo solution will be just any point from this subset of the points on which we computed this MST. So pictorially, here is the set of points, right? So here is one level of the quad tree. So we partition this, right? So each of these parts, right? Each of these parts will go to a different machine, okay? And each machine sees a subset of the points. What does it do, right? Well, it says like, well, given these points, the best thing I can do, I'll just compute the minimum spanning tree on the points that I see. Okay? You say, okay, good, fair enough. Now we need to sketch the solutions, right? So this, we need, there will be another machine that will try to connect all these minimum spanning trees together into one big minimum spanning tree. We cannot send to it all the solutions here because this will take too much space, right? The total number of points is n, right? I mean, we need one machine. So what we'll do, we'll sketch the pseudo solutions here. How do we all sketch? Like, well, I need to connect this tree to the other stuff. What I'll do, I'll tell you one point from my set of points to be connected to the next level, right? So let's say these red points are chosen as the representatives. Right? It says like, look, I have a bunch of points here. They need to be connected to the rest of the stuff. Here is the red point. You can use it as an anchor. And at the next level, the machine will see just the red points, which are the anchors. And say, I need to compute this minimum spanning tree on them. To compute on them, these are the red edges. And this entire thing becomes the minimum spanning tree. Well, becomes a S-spanning tree. Okay, so this is the algorithm, right? I mean, this is an attempted algorithm, as it says up here. It won't exactly work to give what we want, but it's a good approximation. I mean, it's a good start. So first of all, what is the problem here, right? Note that we didn't compute the minimum spanning tree, right? The minimum spanning tree should be, and now colors help me, I guess. Should not have used this edge, but should have used this edge, right? This would have given us the minimum spanning tree. So this algorithm does not produce the minimum spanning tree. I mean, it does something, hopefully, close enough, but it doesn't, right? And what are the troubles? So I'll be done quick. What are the troubles? First of all, the quad tree can cut these minimum spanning tree edges. And this will mean that, the algorithm is forced to do some irrevocable decisions. So in this case, right, so this quad tree, which was say shifted randomly, has cut this edge, right? This edge and this edge, right? So now it sees only three, so this machine sees these 3 points, right? It does not know whether, is it better to connect this point to this one, and this will be connected to something else, or maybe this point should be connected through here, and this point should be left alone, and as it will later be connected to something here, right? So because we have a local view, right, we don't have the entire view perspective of the entire data, we just see a local subset of the points, we just see, we see distorted image. So we might make decisions which are bad, right? Also, there is another problem is how to choose a representative. You can choose really bad representatives. So if instead of in this left bottom part, if the representative was not to be this one, but this one, right, like this, then this would be the minimum spanning tree, which would be even worse, right? So it turns out that one can fix these things. And here is essentially the algorithm. So think about, as before, I mean, these are just to make it slightly more concrete. So imagine every point set is in a cube of size n squared by n squared. One can, ensure that this is the case. We'll impose a randomly shifted quad tree where the cells are of this size. Something. So let me just, show you kind of. So the algorithm is kind of similar to what I said before, with some important key differences, which will give us 1 plus S1 approximation. And here's the differences. First of all, when we compute the minimum spanning tree in one of these cells, right, where we have a local view, we do not compute the entire minimum spanning tree. We just compute minimum spanning tree as long as we use edges up to length epsilon L, where L is the current cell length. Okay? So we do not use, think of this as doing, say, Kruskal algorithm right up to a moment, where at some moment to say, okay, the edges become too long, it will cost us too much to do bad decisions, right? So think it's the philosophy of saying like, well, if I'm doing some bad decisions, at least they shouldn't be too bad, right? So I stop when, doing a bad decision will cost me too much. And the pseudo solution will actually take an epsilon net of the points. So we'll not send just one point, but a bunch of them. Okay. All right. So look, I mean, this is just I'm just describing you the flavor of the algorithm, right? So don't worry if you didn't get all the details. Okay. So so the glimpse of analysis will be really quick. All right. That was the glimpse. So yeah, I want to conclude. Just I ran out of time. Really the message. So actually, the message of the of these two lectures, right, was you gotta love your models, right? So I talked about two models, kind of, right? I mean, these are big models. But one idea is that the models might not be like completely accurate, right? They might not describe precisely what is this, what is the state, kind of, right? I mean, they're not necessarily reflecting the reality of the, all the details of the system precisely, right? But somehow setting a particular model and setting particular constraints does lead to some nice, interesting algorithmic tools that are useful, that become useful, right? So somehow, I don't know, like it's an interesting thing that happens, kind of, right? You set up, something like in physics, right? I mean, we know that Newton's laws are not kind of exactly accurate, right? But they go quite a lot, right? I mean, like it's fine if they're not exactly precise models. We do give nice algorithmic tools, right? And the focus is really kind of, what are the nice algorithmic tools? And I hope I convinced you that, there are some nice things, right, that, would have been hard to come up with, right, if we were just to think about, usually in the standard kind of Turing machine kind of model. Yeah, that's it, I hope. Yeah, I mean, you remember some of these algorithmic tools. And yeah, I mean, they're still in development, as I tried to convey. All right, thank you. Questions? All right, so we can go to the coffee.